Okay, in this lesson, we are going to learn about single replacement reactions. We will be referring to our pink sheets throughout this lesson, so please find your pink sheet and have it ready for this lesson. You should be able to answer these essential questions once you're done watching this video on single replacement reactions. So we're going to take a look at various examples to learn about these single replacement reactions. So our first example, we have solid magnesium reacting with aqueous HCl, and HCl is hydrochloric acid. So we're going to draw what the ions look like in hydrochloric acid, and remember, when I see that AQ, I have something dissolved in water. So I have hydrogen ions, the +1 charge, and chloride ions dissolved in our water. That magnesium originally is by itself in its solid state, in its neutral compound form, not in the aqueous solution to begin with. So when I add the magnesium to this aqueous solution, something really cool happens. I'm going to start to see a bunch of bubbles and gas being formed, and that's because the magnesium is now replacing one of these two ions in our solution. And since magnesium is a metal and metals form positive ions, the magnesium is going to replace the positive ion of our solution. So in other words, that means the magnesium is going to replace the hydrogen ion, and that hydrogen ion gets kicked out of the water, gets kicked out of our aqueous solution. So now the magnesium has taken the spot of the hydrogen, and magnesium forms its predicted magnesium 2+ charge. The chloride is still in the solution. It does not get replaced. But that hydrogen, since now it's no longer in the aqueous solution, it goes back to its elemental form of just hydrogen. But I remember hydrogen is one of those diatomic molecules, one of those Brinkelhoff twins, and it is a gas at room temperature. So those bubbles that I was mentioning, that's the hydrogen gas being produced, and that hydrogen gas is leaving the solution and entering that atmosphere. So if I'm going to write down the products that we have produced, look at what's inside of the water, still dissolved. You have magnesium 2+ and chloride ions. So really you have an aqueous solution of magnesium chloride, and I know magnesium is a 2+, chloride is a 1-, so the formula is going to be MgCl2, and since it's dissolved, it's going to be AQ, aqueous. And I've also produced H2, and that is in the gas state. And I can quickly balance this. We're going to need 2 HCl, so I get 2 hydrogens, and then I got my 2 chlorines over there. Okay, we're all balanced. So how do I look at a balance equation, and especially those reactants, to tell that a single replacement reaction has occurred? Well, the red flag, the key here is to recognize that one of your reactants is going to be a single element, in this case it's a magnesium, and it's taking the spot of one of the elements in the aqueous solution. Magnesium is a metal, so like we said, magnesium can only replace positive ions, and that's going to be the first element in your aqueous solution, in this case the hydrogen. So the magnesium is replacing the hydrogen, producing magnesium chloride and hydrogen gas. Now, why is the magnesium able to replace that hydrogen? And that's because magnesium is more reactive than hydrogen. Okay, and what I have to remember is that those elements that are reactive like to be bonded to other elements. And those elements that are less reactive, they tend not to bond as much, and they tend to just stay by themselves in their elemental form. So here, if we had the option to choose, okay, which one of these magnesium or hydrogen is going to be bonded to something else, we can say that magnesium is more likely to be bonded to the chlorine because magnesium is more reactive. Hydrogen is less reactive, and that's why it's found by itself as hydrogen gas at the end of this reaction. Well, how do I just know that magnesium is more reactive? This is where that pink sheet comes into play. So take a look at your pink sheet. You should have a section on there that says activity series. And we want to concern ourselves for this example right now with the left-hand side. We're looking at the metal side. And the two elements that are involved in our replacement in our example is magnesium and hydrogen. So real quickly, I'm going to locate magnesium and hydrogen on this table. And the way this table works is the most reactive elements are at the top of the list and the least reactive are at the bottom of the list. So remember what this means. Most reactive means, okay, bonded to other elements. These are going to be in your aqueous solutions. So your more reactive elements are more likely to be in aqueous solutions. And those least reactive elements are more likely to be in their elemental form. Okay, not bonded. Or in other words, not in aqueous solution. So looking here, magnesium is found higher on this list than the hydrogen. So that means magnesium is more reactive than the hydrogen. And so since it's more reactive, magnesium is more likely to be an aqueous solution than the hydrogen. So magnesium is capable of replacing the hydrogen in the aqueous solution. So when I read this chart, the element that is higher on this list is capable of replacing those elements below it. So magnesium can replace hydrogen in aqueous solution, but hydrogen cannot replace the magnesium. And that's because magnesium is the more reactive element. Okay, let's take a look at example number 2. I have copper solid reacting with silver nitrate aqueous solution. So I'm going to start here with our aqueous solution and again draw the particles that would be present in the water. We know aqueous means these are really separate ions. So we have Ag with a +1 charge, that ion floating around in the water, and then I have nitrate, -1 ion in the water. And above the water, we're going to be adding solid copper metal. So when copper or any other metal is in its solid state, it's in its neutral state. And we're going to throw that copper into the water. Okay. And I asked myself, well, can copper replace any one of these ions in solution? Now I have to remember copper is a metal, so it only makes positive ions. So can it replace the silver ion here, the positive ion? So I need to look at that pink sheet. I need to look at that activity series. And I find the two elements. I need copper and I need silver. Okay, and remember the one that's higher is more reactive, and more reactive means that that element can replace anything below it. So copper can replace the silver because copper is more reactive, meaning copper is more likely to be an aqueous solution and silver is not. So in this example, copper can replace the silver here. It's going to kick that silver out of the water. So silver is no longer going to stay dissolved in the water. So copper is going to replace that silver. Okay, so copper is going to now become its ion form, copper 2+. Okay, the nitrate stays, nothing happens to it, does not get replaced. But what happens to that silver? Well, remember, silver gets kicked out of the water. It goes back to its elemental form, and it's just going to form silver neutral atoms, or silver Ag. Okay, but I'm not going to write a charge on it because now it's in its solid state. Not its aqueous state, but solid state, so there's no charge on it. And the reason why I'm drawing at the bottom of the beaker is because it's going to be a solid, and that's going to collect at the bottom of the beaker. Okay, it's not going to escape the water like a gas, but it's going to fall to the bottom. So what do we have here on our product side? Again, what's still dissolved in our water as part of our aqueous solution? I look at the ions that are floating in the water. I have copper 2+, and I have nitrate ions. So I have really copper and then nitrate. There's going to be 2 nitrates because I need to cancel out those charges. And since this is dissolved in water, this is going to be my aqueous solution. And the other thing that we made was silver solid. I can quickly balance here. I need 2 there, and 2 there, and I have my balanced equation. So again, though, look at your overall equation. How do you tell that this is a single replacement reaction? Again, I have a single element by itself, and look at what that single element has done. Since it's a metal, it forms positive ions, and it potentially can replace the positive ion of our aqueous solution. Again, yes, this can happen because on our activity series, copper is higher on the activity series, meaning copper is more reactive and can replace the silver in our solution. And so now it's the copper that's bonded to our nitrate because copper is more reactive. It likes to bond to things. And the silver is now by itself because it's the less reactive metal, and less reactive metals are going to tend to stay in their elemental form, not bonded to anything else. So now I would like for you to go back and answer these essential questions. Okay, how do you know, or how does the more reactive element behave? Think about what the magnesium and the copper did. Number 2, how does the less reactive element behave? Okay, think about how that hydrogen and the silver behaved. And number 3, how do you determine which element is more reactive? What did we have to look at? What did we have to examine to tell that something is going to be more reactive than something else? Number 4, what type of ions do metals replace? So think about what type of ion the magnesium replace and what type of ion the copper replace. And finally, number 5, how can you tell by just looking at the reactants that a single replacement reaction is going to be possible? So please take a moment, jot down your answers to these questions, and I hope you learned something about single replacement reactions.